12-meter long ladder is leaning against a vertical wall. The ladder begins to slide down the wall. When the top end is 6 meters from the ground, it is sliding down at 4 meters per second. How fast is the bottom moving away from the wall at this time? So let's draw a diagram real quick. Okay, so we've got a wall. This is kind of the ground here, and the ladder is going to go from here to there. All right. Now we know this ladder, the length of this ladder is 12 meters. Okay, and let's call this, let's label this as Z. Okay, this here. And so this distance here would be X, and this is Y. Now the ladder begins to slide down the wall. So this kind of top end of the ladder is moving down this way, which means that as this moves down, this part here should be moving towards the right, right? Okay, so it's sliding down. The top end is 6 meters away from the ground. When that's happening, it is sliding down at 4 meters per second. So dy, okay, over dt, the rate of change in this distance right here, okay, is minus 4 meters per second, yeah, because it's shrinking, so it's negative, okay? Now, what are we looking for? We're looking for how fast the bottom is moving away, so how fast this length here, this x, is increasing, right, when the top end is 6 meters from the ground. So we're looking for dx over dt equals what? Okay, when y equals 6. Okay, so let's write my formula here real quick. Do we know any formula that relates this y, this x, and this z, which are the three things that we kind of either have information about or they're asking about, right? And by now you should know that, you know, x squared plus y squared is equal to z squared, right? From Pythagoras, okay, because this is a right triangle. So some of you, okay, might try to plug this y equals 6 into here, and you should not be doing that because this y, as you can see, is changing over time. And when something is changing over time, we can only plug it in after we've taken the derivative, okay? Don't plug it in right away because it's not always going to be true. What is going to be true and stay constant throughout the whole problem is the length of this ladder, right? No matter, you know, where this ladder is, okay, no matter how far it's slid down, the length of this ladder is always going to be 12, okay? So if something is constant throughout the whole problem, you could plug that in, okay? So we can replace the z squared here with a 12 squared, okay? So now we can differentiate both sides, okay? So don't forget that we're using implicit differentiation here, right? So as we take the derivative of this guy, we're going to get 2x dx over dt, okay? And we're going to add that to the derivative of this, which is going to be 2y dy over dt. And on the right side here, the derivative of 12 squared, that's a constant, that's going to be 0, okay? Now let's look through what we know and what we don't know. We don't know what x is, okay? So this is still like a question mark here. This dx over dt, well, we don't know it, but that's all right because that's what we're looking for. So it's okay that we don't know it. This y right here, we can plug this y equals 6 in now, right? We've taken the derivative, we can plug this in. So y, we're good. dy over dt, we know is negative 4 meters per second. So we're also good on that front. But we don't know what this x is. So what we can do here is kind of draw another triangle. Okay, so let's draw a triangle like this, and like this. Okay, now we know we're looking for dx over dt when y equals 6. So we can put 6 right here, and this is still 12, right? We said this is going to be constant the whole way through. And we're now looking for what x is when y equals 6. Well, we can find what x equals to, right, when y equals 6 using Pythagoras once again, right? So if we just kind of do the reverse of Pythagoras, okay, you're going to get that x is equal to the square root of the hypotenuse squared minus 6 squared. Okay, so 12 squared minus 6 squared, that's going to come out to the square root of 108. Great. So you know x is the square root of 108. That's not a very nice root, so that's all right that we don't write it, okay? And so now let's go back over here, okay, and plug that in. So we've got 2 times the square root of 108, okay, dx over dt. And here, let's make it equal to negative 2. Y we know is 6, and dy over dt we know is going to be negative 4, okay? And so finally, dx over dt is going to be equal to minus 2 times 6 times minus 4. Okay, let's put the brackets here, I guess. And that's all divided by 2 times the square root of 108. That's going to come out to approximately 2.31 meters per second. And that makes sense that it's positive because this x here, this length, is increasing. Okay, so that's the answer for question A. All right, question B. So Arbor and Caden are on bikes and are at the same place. Arbor starts riding directly north at a rate of 8 meters per second. 5 seconds after, Caden starts to ride directly east at a rate of 5 meters per second. At what rate is the distance between the two riders increasing 20 seconds after Caden started riding? So let's say they both started like, let's grab this right here. Okay, let's say they both started riding right there. Okay, well, actually, let me actually draw a little bit nicer. Okay, right there. That's where they started. And Arbor starts riding his bike this way, north, right? And Caden starts riding east. I can't say that way. Okay. And we're looking for this distance right here between the two of them, right? This one. Okay. So let's call this y, let's call this x, and let's call this z. Okay. And we know that Arbor is riding north at a rate of 8 meters per second. So this kind of vertical kind of distance right here, this length, is increasing at a rate of 8 meters per second. So dy over dt is positive 8 meters per second. And we know that this x, this horizontal distance, is growing at a rate of 5 meters per second. So dx over dt is equal to 5 meters per second. Okay? Now, if we think about this, what formula do we know kind of ties these three things together, right? Which, these three things being the kind of variables that we've been given information about, or we're kind of asking about, right? Which, we've given some information about y, x, and we're asking about z, okay, how fast z is changing, right? Let me write that down, actually. We're looking for the rate of change of this distance. So we're looking for dz over dt, okay? Equals what? 20 seconds after. Okay, so let's write a formula that ties those three things together. And we know by now, okay, Pythagoras, right? X squared plus y squared is equal to z squared. And that kind of involves and encapsulates those three variables. Okay, so let's take the derivative with respect to time. You're going to get 2x dx over dt plus 2y dy over dt is equal to 2z dz over dt. So, we know about dx over dt, and we know what dy over dt is, okay? But we don't know what x, y, and z are, right? So this is like, yeah, we're good. Yes, we're good. This we're looking for, so that's okay. But we still don't know what these three things are. So what other information in the question can we use to help solve this question? Well, we know, we're looking for dz over dt 20 seconds after they both started riding. And we know how fast they're going. So if we draw a little new triangle here, okay, let's say this is 20 seconds after they started riding, right? Well, if we know that they've been riding for, this is 20 seconds after Caden started riding, which means, 20 seconds plus 5 seconds, right? Because Arbor started riding 5 seconds before Caden did. So Arbor's been riding for 25 seconds. And if he's going 8 meters per second, then y is just 8 times 25, right? 8 meters per second times 25 seconds, which comes out to 200 meters, okay? And similarly, x, okay, Caden's been riding only for 20 seconds, okay, and he's riding at a rate of 5 meters per second. So 5 times 20, that's going to come out to 100 meters, okay? So x is 100, y is 200, and now we can find out what z is using Pythagoras, right? So 100 squared plus 200 squared is equal to z squared, right? So if we just plug that into our calculators, you should get that z, okay, after a bit of solving, z is equal to 223.6 meters. Okay, so this is 223.6. And so now we know x, we know y, we know z. We can fill out this equation. Okay, so let me scroll down a little bit here. Okay, so we have a bit more space to work with. So 2 times 100 times this dx over dt, we said it was 5, plus 2 times y is 200, okay? dy over dt is 8, is equal to 2 times 223.6 dz over dt. So on the left here, you're going to get 4,200 is equal to 447.2 times dz over dt. And so if you just do 4,200 divided by 447.2, you're going to get 9.39 is equal to dz over dt. Okay, and that's the answer for question B. Or at least I should add my units here. It's 9.39 meters per second. And that's your answer for question B. Okay, Cole and Nick are 50 feet apart. Nick starts walking north so that the angle shown in the diagram below changes at a constant rate of 0.02 radians per minute. So that's actually d theta over dt, right, is 0.02. And we want to know at what rate is the distance between the two people changing when theta is 0.5. So we're looking for dx, over dt, right? When theta equals 0.5. Okay. Now, this theta is changing over time, so we can't plug in theta equals 0.5 into whatever formula we come up with yet, okay? But what we do know, what is going to be constant, is this thing here, right? This distance at 50, okay? So whatever formula we come up with, we can plug in that 50 right away, but not that theta equals 0.5. So let's think about this. Do we know any formulas that relate this kind of hypotenuse to this angle's kind of adjacent side? Well, if you think back to trig, you should kind of remember that cos of an angle, right, cos theta, is equal to the adjacent over the hypotenuse, right? So that's 50 over x in this case, which we can kind of simplify to 50x to the minus 1, okay? And so now we can take the derivative of both sides. So here we're going to get minus sine theta d theta over dt is equal to 50 times minus x to the minus 2 dx over dt. All right, now this sine theta here, we can plug in that theta now because we've taken the derivative. So this is sine of 0.5 radians. D theta over dt, we have that over here, that's 0.02. Okay, here we've got 50 times minus x to the minus 2 dx over dt. I don't know what this hypotenuse is yet, right? I don't know what that is, but I know that theta is 0.5 radians. So let's kind of draw a line here, okay, and see if there's anything else we can do using the information in the question, okay? So let's draw a triangle, and we know this is always going to be 50, yeah? And we know this theta now, okay, in the time that we're looking for, this is going to be 0.5. And this is still going to be my hypotenuse. We're going to call that x. All right. Now, we can just use that same formula that we had before. We know cos theta, but now theta is 0.5, right, is equal to 50 divided by x, right? So now if we just kind of cross multiply here, okay, we know that x times cos of 0.5 is equal to 50. So x is equal to 50 divided by cos of 0.5. And so you should get that x is equal to 56.97. Okay, so I'm going to scroll down a tiny bit here. All right, now we can plug in this 56.97 into that x. All right, so on the left-hand side here, if we kind of multiply this out, you're going to get something along the lines of negative 0.00959, and you're going to divide by whatever 50 times negative 56.97 to the minus 2 is, okay? So 50 times negative 56.97 to the minus 2, and that's going to be equal to dx divided by dt. So punch that into your calculator, and you're going to get that dx over dt is equal to 0.622 feet per minute. All right, question D. So Mr. Hum is walking towards the door of his classroom at a rate of 1.2 meters per second. At the same time, Laura is walking down the hallway, which runs perpendicular to the door. Okay, so let's actually just try to visualize this real quick here, okay? So we've got, let's say, a hallway here. Oops. Got a hallway over here, right? And we've got, let's say, a classroom here, okay? Like this. That's the classroom. And so I'm walking towards the door this way, and Laura is walking down the hallway that's perpendicular to the entrance of the classroom, right? Perpendicular to the door, and she's walking away from the classroom. So let's say she's over here, she's walking this way. Okay. Initially, Mr. Hum is 6 meters away from the door, and Laura is 8 meters from the point in the hallway directly in front of the door. So let's say this distance right here, okay, is 8, and this distance right here, that's 6. Okay, this is not drawn very accurately, but let's pretend it is. Okay, and we want to know how fast is the distance between Mr. Hum and Laura changing 4 seconds after they started walking. So we're looking for the distance from Laura to Mr. Hum, which is kind of like that hypotenuse that you can imagine here. Okay, kind of something like this. Okay, so once again, okay, I mean, we're dealing with kind of this axis, and then this kind of hypotenuse thing here. So if we had to guess, right, we're probably gonna have to use Pythagoras kind of later on in this question, but let's write what we know so far. Okay, so Mr. Hum is walking towards the door at a rate of 1.2 meters per second. So this kind of distance right here, let's call this this distance horizontal distance. Okay, that's the x. Okay, and so dx over dt, that distance over here is shrinking, right? As I get closer towards the hallway, this distance, okay, is shrinking. So it's going to be minus 1.2 meters per second, right? dy over dt, however, okay, as Laura is walking away from this door here, this vertical height is increasing, right? So this is going to be positive 1.5 meters per second. Okay, and we're looking for dz over dt, okay, 4 seconds after they've started, 4 seconds later, okay, 4 seconds after they started moving. Okay, so let's scroll down a little bit so I have a bit more room to work with here. Okay, let me add units here as well. Okay, so once again, we're probably, like I said before, we're gonna probably use Pythagoras. So let's write that down. Okay, so x squared plus y squared is equal to z squared. And now we can differentiate. So 2x dx over dt plus 2y dy over dt is equal to 2z dz over dt. Okay, so we know this, right? That's up here. We know this, so we're good. And we're looking for dz over dt, so it's okay that we don't know what that is. But we don't know what this is, we don't know what this is, and we don't know what that is, right? But what we do know is this is 4 seconds after that, after they've started moving, right? Okay, so let's draw a little line here. We're going to do a little bit of work on the side over here, okay? Now, initially that distance, that x, right? Initially it was what? It was 6 meters, right? And if I'm walking at a rate of 1.2 meters, then I've closed how much distance? Well, the amount of distance I've moved, right, is going to be 4 times 1.2, which comes out to 4.8. So the amount of, horizontal distance left is going to be 6 minus 4.8, right? So it's the initial distance minus the amount of distance that I've covered, how much distance I've walked in those 4 seconds, which comes out to 1.2 meters. That is my x, okay? And Same idea for Laura here, okay? So how far has she walked? Well, in those 4 seconds, walking at a rate of 1.5 meters per second, we know that she's walked 6 meters, right? And so if she was initially 8 meters away from the door, so she's over here, okay, now she's walking away, so it's going to be 8 plus those 6 meters that she's covered in those 4 seconds. That's going to be 14. That is equal to y, okay? So I've got my y, I've got my x. Now I'm going to draw, let me scroll down a little bit more. Okay, let me draw another triangle here, okay? It's a new triangle. And this is 1.2, and this is 14. And using Pythagoras, we can find what z is, right? This kind of hypotenuse here, okay? And that's going to be the square root of 1.2 squared plus 14 squared, right? And if you punch that into your calculator, you should get something like 14.05 meters, okay? And so that's your z. So let's go back up here and plug that in then, okay? So we've got x is 1.2, so this is going to be 2 times 1. Well, actually, let's use my original color here. So 2 times 1.2, okay? I know dx over dt is negative 1.2 meters per second, right? Plus 2 times y, which is 14, okay? dy over dt, that's going to be positive 1.5, and that's going to be equal to 2 times 14.05, and here we have dz over dt, which we're still looking for, okay? Now let's simplify this left side a little bit here. So 2 times 1.2 times negative 1.2 is about, it's going to be negative 2.88 plus, here we've got 2 times 14, so that's 28 times 1.5, that's going to be 42. And here we're going to have 28.1 dz over dt. So all we got to do is add this up and then divide by 28.1. So that's going to come out to 39.12, and we're going to divide that by 28.1, okay? And that's going to be 1.39, and that's your dz over dt, okay? And your units here is meters per second.